Hi, it's me again, Dane Quinn from the University of Akron, and I'm back. I'm back for today's video lecture on the equations that will describe velocity of mechanisms. So we know that the loop closure equation describes the essential kinematics and the configuration of a mechanism. The constraints, the connections between the links, basically the essential kinematics of the system. So if we have a loop closure equation, it's valid at any time. For the 4-bar linkage that we see on the right, our loop closure equation can be written as the vector from O2 to A plus the vector from A to B, so that would be R of B with respect to A, equals the vector from O2 to O4, right, or R of O4 with respect to O2. And then finally, R of B with respect to O4. So again, this is our loop closure equation. It's always true. As this mechanism moves around, as say link 2 rotates over, this still holds, which means that the change in each one of these vectors must be consistent with this equation. So in particular, if I were to take a derivative of this entire equation, then the resulting equation would have to be valid. So the change in R of A with respect to O2 plus the change in R of B with respect to A has to be equal to the change in O4 with respect to O2 plus the change in B with respect to O4. Again, if this didn't work out, then while we might have something that was true now, if these changes don't all work out and are consistent with one another, then at some later time, this wouldn't be a true statement. So again, the change in the components, they must be consistent with one another. Now, I will notice that this vector from O2 to O4 never changes, right? So this term is actually equal to 0. So if I were to sort of go and draw this equation, right? I mean, this is geometry. This is a vector equation. It has some sort of geometrical understanding. Then the change of A with respect to O2, right? So maybe that's this vector. Right, so we'll say that this is the derivative of R of A with respect to O2 plus then the change in, say, the second part, d dt, B with respect to A. Well, that has to be equal to the change in B with respect to O4. Again, here this piece vanishes because this is a constant vector. So if I look, we have a vector equation. The derivative of the position of A with respect to O2, which might be given here in blue, plus the derivative of B with respect to A, given as this red vector, has to be equal to the derivative of B with respect to O4. Again, we've seen lots of vector equations so far, mostly dealing with position and configuration. But when we move to velocity, we once again are facing a vector equation that needs to be solved. So again, looking at this mechanism, I can go through and define the loop closure equation, and that's here L2 in the I2 direction, plus L3 in the I3 direction, L1 in the I direction, and L4 in the I4 direction. So we've seen lots of 4-bar linkages at this point, right? So this should be fairly comfortable for you. When I take a derivative of this equation, then I'll just take the derivative of each individual term. So these all look very similar, right? So let me just consider one term. And let's start off and look at the derivative of L2 I2. Well, the product rule says that that's going to be the derivative of L2 with respect to time in the I2 direction, plus L2 times the derivative of I2 with respect to time. And the derivative of I2 with respect to time is the angular velocity of link 2 cross I2, right? So essentially it's how fast I2 spins. Well, omega 2 is theta 2 dot in the k direction, right? So theta 2 dot is how fast this direction in particular spins, and it's in the plus k direction if theta 2 dot is positive. Looking at omega 3, again, theta 3 is defined positive counterclockwise. So that's theta 3 dot in the k direction. And likewise for omega 4, theta 4 dot in the k direction. If any of these were defined positive clockwise, then their angular velocities would be in the minus k direction. So, going back to this term, we see that we have the derivative of L2 with respect to time in the I2 direction, plus L2 theta 2 dot k cross I2. And here, L2 is constant. So this term drops out. Evaluating the cross product, k cross I2 is equal to J2. So we end up with L2 theta 2 dot in the J2 direction. So that's just this one term. And we can go through and do the other terms in a similar fashion. Again, remembering that this term is equal to 0 because L1 is constant and I is constant. You know, essentially, here you could go through and say omega 1 is equal to 0 if you want to be consistent with the way that we've done everything else, because I is not spinning, right? So its angular velocity is 0. And as a result, the vector velocity equation reduces to this first term we already said was L2 theta 2 dot in the J2 direction. This next term we would work out and find that it's L3 theta 3 dot in the J3 direction equals, this was 0 plus L4 theta 4 dot in the J4 direction. Now, I would urge you maybe to pause the video at this point and go through and work these other two out. And I do want you to remember that although these look very similar, they look very similar because we have defined theta 2 and theta 3 and theta 4 in a similar way, right? They're all positive counterclockwise. They all describe the orientation of links with fixed length and so forth. One of the things that I want to stress to you is that when you set up your kinematics of mechanisms, you may not set them up in exactly the same way every single time. So I really want you to get comfortable working through all of these various steps as opposed to just remembering what you did last time. So every time you go through and you look at one of these velocity equations, find the loop closure equation. Actually take the derivative of each one of the vectors and see what it is. Depending on how you set up your coordinates, depending on the problem, right? Different terms may look different. And that's okay. We want you to be able to set your problem up in the way that's most convenient for you rather than trying to make it fit into some predetermined framework that someone gave you one time. I want you to be able to look at a problem and solve it. So again, even though these all look similar, I want you to understand why they look similar so that if things are different, you can still solve the problem. Okay, let's go and look at the next part, which is basically trying to solve this. So here again, we have our loop closure equation, and it relates the position variables. Those would be theta 2, theta 3, and theta 4. Oftentimes theta 2 is known, solve for theta 3 and theta 4, perhaps. Take the derivative, and we get the velocity equation. And that introduces our velocity variables, which are the theta dots in this case. Theta 2 dot, theta 3 dot, and theta 4 dot. This, again, is a vector equation, right? So it has two scalar components. And we can pull off two independent scalar equations from that. And the unknowns here, or the variables, the velocity variables, are theta 2 dot, theta 3 dot, and theta 4 dot. So again, it's a 1 degree of freedom system. I would tell you one of these things, oftentimes theta 2 dot, and that would allow you to solve for the remaining two velocity variables. But I'll note that the velocity equation doesn't just contain the velocity variables. Instead, it contains both position and velocity variables. So really, if you just look at this, you actually have 6 variables. You have the 3 velocity variables and you have the 3 position variables. Well, the way that we get around this is that we solve the loop closure equation first for the position variables. So I go back up here and look at the loop closure equation, solve for, say, theta 3 and theta 4 in terms of theta 2. And then once I have that, those are now known in the velocity equation. So once we solve for the position variables, then we can go and solve for the velocity variables. But you can't tackle this equation directly at the very beginning without knowing the position variables, because you would just have too many unknowns. So that's kind of the procedure here is we solve for the position, and then we turn and solve for the velocity. Again, this vector equation has a geometric sort of interpretation. And again, it's L2 theta 2 dot in the j direction. Now, assuming that I've already solved for the position variables, I actually know the direction of this term, right? So this would be the J3 direction. And then this would be the J4 direction. Again, let's assume that we've already solved for the configuration of this mechanism. This is the J3 and that's the J4. So I'm asking, can we take this known vector, which is the input velocity vector, add something in the J3 direction, and end up with something that's only in the J4 direction? And you can obviously see how this works, right? We basically add this vector to get this vector. Anything else that we were to add in the J3 direction would not lead to a resultant that was only in the J4 direction. All right, so here this is L3, theta 3 dot, J3, and this would be L4, theta 4 dot, in the J4 direction. Geometrically, essentially, the value of theta 3 dot and theta 4 dot, these values that we're looking for, are related to the lengths of these vectors. And that would actually compose a graphical analysis of this mechanism. So here, let's sort of carry this through a little bit further on this 4-bar linkage, and I want to focus on solving for the velocity variables. So I'm going to assume that we have already solved for the configuration. Right? So I know theta 2, theta 3, and theta 4, which means that these directions are assumed to be known. And then I'd like to find theta 3 dot and theta 4 dot. Right? So let's assume that theta 2 dot is given. This is our input velocity variable. So now I have a vector equation. If I want to solve for theta 4 dot, well, our procedure, as we've seen previously, is to actually eliminate theta 3 dot. And as a result, whatever's left will give us a single equation on the unknown that we're interested in. So again, our equation is L2 theta 2 dot in the J2 direction, L3 theta 3 dot in the J3 direction is equal to L4 theta 4 dot in the J4 direction. So if I want to eliminate theta 3 dot, well, that's in the magnitude of this term, so I'll dot with a perpendicular direction, namely I3. And of course, we've already solved for these position variables, so all these directions are known, and I can do this. It gives me L2 theta 2 dot times I3 dot J2. Here, this term, I3 dot J3 is equal to 0. And then on the right-hand side, I get L4 theta 4 dot I3 dot J4. So, look, we can work this out. We can solve for theta 4. Well, theta 4 dot. And theta 4 dot here is equal to L2 times I3 dot J2. Well, I worked this out. I would urge you to pause the video, go through and write these directions in terms of theta 2 and I and J and theta 3 and theta 4, and then take dot products. And what you get is sine of theta 3 times cosine of theta 2 minus cosine of theta 3 sine of theta 2 divided by L4 times I3 dot J4. Well, again, pause the video, work it out, and you get sine of theta 3 cosine of theta 4 minus cosine of theta 3 sine of theta 4 times theta 2 dot. Or if you are, if you recognize this, this becomes L2 sine of theta 3 minus theta 2 divided by L4 sine of theta 3 minus theta 4 times theta 2 dot. So we're able to, again, with this vector equation, eliminate theta 3 dot and then solve for theta 4 dot in terms of theta 2 dot. Again, this input speed of link 2, maybe it's the known quantity, and we're looking for the output speed of link 4. If you want to go and find theta 3 dot at this point, my recommendation would be to go back to the loop closure equation in terms of I and J. I mean, since you know theta 4 dot, and you've just solved it, and theta 2 dot was input, right? Now, regardless of which component you take, you just have theta 3 dot. Now, for example, using the J direction, we would get theta 3 dot equals L4 cosine of theta 4 times theta 4 dot, right? But we already know that. Minus L2 cosine of theta 2 times theta 2 dot, right? And that would be that term, divided by L3 cosine of theta 3. So we solve for theta 4 dot in terms of theta 2 dot, and then we use that to solve for theta 3 dot. One important point of all this is that the velocity of a mechanism depends on the configuration So it's not enough to say, oh, the input velocity of this link is, whatever it is. But you also have to know where the mechanism is in order to determine the velocity variables. So, for example, again, this is what we had for theta 4 dot. I will note that if sine of theta 3 minus theta 2, right, so that's this piece in the numerator, is equal to 0, which implies that theta 2 and theta 3 are equal, or theta 2 is equal to theta 3 plus 180, then theta 4 dot is equal to 0. So if links 2 and 3 are parallel, whether they're in the same direction or directly opposed from one another, that would imply that the output angular velocity would be equal to 0. Well, this would be one of the limit positions of the mechanism. And it's a geometrical thing, right? It comes from geometry, but it's really easy to identify those limit positions, for example, using the velocity. Now, the other thing that we'll notice is that the output velocity variables, well, they are proportional to the inputs. What that means is that they scale. If we double the input, I would double the output. Now, there is this sort of coefficient in front of this that depends on the configuration, but at a given configuration, the input and output angular velocities, for example, are linearly related. So looking at an example here, just to finally kind of close this, let's take this 4-bar linkage that we've shown here. I'll let L1 be 125 centimeters. L2 is a little bit shorter. L3 is fairly long, 200. L4 here is 175. And at this instant, I will go ahead and solve for the configuration variables. So let theta 2 be equal to 60 degrees. Theta 3 is 11.49. Theta 4 is 46.26 degrees, whatever. So again, I have basically given you the mechanism and given you the configuration variables. Well, then we can relate the velocities. So at this configuration, and I want to emphasize that the velocity depends on the configuration, right? So if we change the input angle, then the way that theta 2 dot and theta 4 dot were related would be completely different. But at this input configuration, theta 4 dot is, if I go and use this relationship that I developed, 0.751 times theta 2 dot, right? So again, they are linearly related. And I can also go and then solve for theta 3 dot. Theta 3 dot here is equal to 0.671 times theta 4 dot minus 0.255 theta 2 dot. And again, that came from this relationship on theta 3 dot that we found from the j direction. Coincidentally, if we had used the I direction, we would end up with something that looked different, but it would actually give us exactly the same answer. And finally, putting this together, theta 3 dot is 0.209 times the input angular speed. So here we have determined how we identify the velocity equations for a mechanism. And essentially we take the loop closure equation that is valid for any time, and we evaluate how those individual terms change. Because it's valid for any time, then kind of the total change of the equation, right? They have to be consistent with one another. And that then provides us with velocity equations. This should also give you a hint as to how we will ultimately get acceleration equations. We'll just take the derivative of velocity, which really we've already learned how to do. It's just another vector equation, and we'll evaluate the change in that. But that's for another lecture. So that's it for today. Thanks, and I will talk to you again. Bye.